Okay, it's time to discuss acids and bases. Recall from General Chemistry 1, acids are those compounds that dissociate in water to give you H3O+. Then we talked about it as H+, and then in Gen Chem 2, you were told that H+ reacts with a molecule of water and generates your hydronium ion. So, really, hydronium ion and a proton are one and the same thing provided your medium is an aqueous medium. Bases, on the other hand, usually will dissociate to give you hydroxide ions. Now, these two definitions of an acid and a base, these were given by Arrhenius. So these are the oldest definitions of acids and bases, and later Bronsted and Lowry and Lewis provided more newer, more broader definitions of acids and bases, which we are going to refer to in a little bit. I also recall from General Chemistry 2 that depending on your concentration of the hydronium ion and the hydroxide, you would be able to determine the pH. And the whole basis for that particular concept lies in the fact that Kw, the ion product, which is nothing but the product of hydronium ion and the hydroxide, is nothing but a constant 1.0 times 10 to the negative 14. So if you knew the hydroxide concentration, you can use this formula to determine the value for hydronium ion and vice versa. Now, if you take log of this equation, let's call that equation 1, and now I take the log of this particular equation on both sides, you would say negative log of H3O plus negative log of hydroxide negative. Hopefully you can recall from school mathematics that when there is a product sign in terms of logarithmic scale, it gets converted into an addition sign, and that's going to be equal to negative log of 1 times 10 to the power of minus 14. Negative log of hydronium ion is nothing but pH, because the small letter p is defined as a negative log of whatever follows it. Negative log of OH negative is going to be written as POH, and the right hand side is going to end up being 14. And that is the reason why your pH scale varies between 0 and 14, 7 being neutral. Any number more than 7, that is between 7 to 14, is going to be an alkaline solution, and any number between 0 to 7 is going to be considered an acidic solution. Now, another thing to keep in mind is when you're thinking about getting the pH, recall from General Chemistry 2 that the strength of the acids and bases plays a very important role in determining what the pH is going to be. So if you have a strong acid or a strong base, in that case you would consider that that particular compound is going to remain completely 100% dissociated. What I mean by that is that if you take, let's say, 1 molar solution of HCl. Now, HCl is hydrochloric acid, and you know that it's a strong acid. So when you take 1 molar solution of HCl, which means that you basically took 1 mole of HCl and you dissolved that in 1 liter of solution. So in that particular situation, what's going to happen is the HCl is going to get dissociated into H plus and Cl minus, and then that would mean that if you began with 1 mole of HCl, it would end up giving you 1 mole of H plus and a mole of Cl negative in that liter solution. So if you're considering strong acids and strong bases, those are going to remain 100% dissociated. On the other hand, if you have a weak acid, just such as acetic acid, that's going to be slightly weaker, and there are reasons for it. And in this particular course, in this chapter, we are going to visit some of those reasons. Like I said, Arrhenius's work was the most original, also the most primitive of all the definitions of acids and bases. The second one was given by Bronsted and Lowry. And according to them, so let's write somewhere what Arrhenius said, and let's see how similar or different Bronsted and Lowry's work was. So I'm going to say Arrhenius, he defined acid as a proton donor and a base as a hydroxide donor. Okay, and this is Arrhenius. And now we are going to talk about Bronsted and Lowry's work. And what they said was that an acid can donate a proton. So they sort of retained their definition of Arrhenius's acid. So an Arrhenius acid and a Bronsted-Lowry acid are exactly the same thing. However, they defined a base as something that will accept a proton. So their point of reference for any reaction was the proton, and they really considered an acid-base reaction to be a reaction which involves a transfer of a proton, something that donates the proton, and another species that's going to accept the proton. So in that sense, you can perhaps envision that Arrhenius is defining his bases as hydroxide donor, but Bronsted and Lowry would call that same base a base because that hydroxide, the OH negative, will have the capability to accept a proton, and we will see in a second how that would happen. Over here in this reaction, you are seeing some compounds which are reacting with each other, and they are generating two other species. So you have acetic acid, which is reacting with methylamine to give you methyl ammonium cation and the acetate unit. So between acetic acid and methylamine, hopefully you can see that acetic acid is going to be the acid component. Methylamine, which is very similar to ammonia, and you know from general chemistry too, that ammonia is a base, so methylamine is a base as well. What becomes of the acid upon the loss of that proton? Which proton am I talking about? This proton right here. So the loss of that proton is going to give you a conjugate base. The gain of that proton is going to give you a conjugate acid. Now, even if you forgot in a test, let's say you did not know acetic acid is acidic, as long as you can at least know the definition of an acid, that it will donate a proton. So if you're comparing acetic acid, which has a proton over here, and the acetate unit has lost that proton, so that would mean that that proton has been donated, and that makes the first species acidic, and what becomes of an acid is a conjugate base. An acid is always going to react with a base, which is why on the left hand side of this reaction you have an acid and a base. Likewise, on the right hand side you have another acid and a base. So at any given point of time, you are going to see a pair of acid and base on either side of the reaction. Now, this type of a reaction will always contain two sets of conjugate acid-base pair. What do I mean by that? Notice I have acetic acid as the acid. Its corresponding conjugate base is the acetate anion. So we would say that the first pair is acetic acid acetate unit. So CH3COOH CH3 COO negative. That's my first acid conjugate base pair. The other one will be the methylamine, CH3NH2, CH3NH2, and that is reacting to give you CH3NH3 plus. And so that is your second pair. So at any given point of time, you will see two sets of such acid-base pairs. Another thing you should observe, another thing you should notice here is that an acid either contains protons or is positively charged. So notice acetic acid that contained the proton and ammonium ion has a positive charge. So the acid is going to contain a positive charge. The base is going to act as source of electrons, and so that's going to contain either the source of electron or the negative charge, and that would make it a good base. I am going to spend some time going over all the aspects that can be used to define what's an acid and what's a good base, but for now realize positive charges or neutral species which are deficient in electrons are acidic in nature. On the other hand, negatively charged species or neutral particles which contain lone pair of electrons will be considered basic in nature. This slide carries several examples of acid-base pairs, and so you can see HCl, which we expect to be a proton donor, and you can compare as to what it is right now and where that's going. So you can see that the Cl and the H dissociated, so HCl must have acted as a proton donor, and the hydroxide essentially picked up that proton to form water. So one might be able to write down this in an ionic form as HCl plus OH negative gives you Cl negative plus H2O. And that would mean that HCl is your acid, OH is your base. What becomes of the acid is a conjugate base. What becomes of the base is a conjugate acid. So now if you compare, the negatively charged species are either bases or conjugate bases. The stuff that contains the proton, so HCl over here and water over here, are my conjugate acids. Likewise, if you consider H2SO4, that's going to be your proton donor. That is going to donate a proton to ammonia. Ammonia is going to become ammonium ion, and a bisulfate ion is going to get generated. You've seen some of these reactions in general chemistry too, by the way. Let's take a look at something that's organic now. So we have HCl, which is treated with an alkene over here, and it's forming a positively charged species. The way the reaction will go is whenever you have to show a reaction mechanism, you always show it through electron arrows, and every arrow essentially signifies two electrons, one for this side, the other for this side. So if you are showing an arrow like this, that would mean that it's a single electron. So here you would say that it's a pi system. So there are two electrons. Both of those electrons are going to be given to the proton. Chlorine would leave, and your product is Cl negative and the carbocation. So if somebody asks you what's the acid, what's the base, well, HCl is the one which is the proton donor, and so you would say that it is an acid, and of course an acid is going to react with a base. So this is acidic, this is basic, since that's going to accept your proton. What becomes of the acid? So HCl is getting converted to Cl negative. That will be your conjugate base. What becomes of the base, which was the alkene, and it's forming a carbocation, and that's going to be called as the conjugate acid. Please realize the word carbocation. We have seen this before, but I'm just reminding you. Carbocation, the word is derived from cations being positively charged, and since that positive charge is being held on a carbon, we call it a carbocation, which always is sp2 hybridized. So let's say you have a CH3, you have a CH3, and maybe you have a CH3 here. Positive charge is held on an empty p orbital. Carbon, as you know, can form 4 bonds. So 3 are going to 3 different carbon atoms, and the positive charge is on the carbon. So this is a planar shape, and we use the word carbocation to define that. The other ion that is possible is carbon ion. And in case of carbon ion, you have CH3, let's say, with a negative charge here. That would mean that there is an additional electron. So additional electron on carbon. Okay. So at this point of time, you probably should connect with the general chemistry 2 concepts on acid dissociation constant, the base dissociation constant, which basically signify they give you information about the strength of an acid. Strength of an acid. And there we learned that higher is this value, essentially that particular acid is going to be strong. So what I mean by that is that if you consider, let's say CH3, COOH, and you treat it with water, and that gives you acetate and hydronium ion, right? So you would say that in this particular case, you have, you can write down the equilibrium constant as concentration of the acetate times concentration of the hydronium ion. So those are my concentration of the products. And we divide it by the concentration of acetic acid. We are going to leave water as is because that's a liquid. Everything else is a solution, so that's aqueous. So we are going to count that. So only AQ and G for gases, they are counted. Solids and liquids are not counted. Recall that rule. In this particular case, we can say that the K is a specific K. It's called actually a Ka for acid dissociation constant. So having a large value of Ka basically tells you that the numerator is much higher as compared to the denominator. And so that would mean that most of your acid remains dissociated. What does that ultimately culminate into? It culminates into an idea that you have a lot of hydronium ion that is present in your reaction mix. So higher values of Ka would mean that you have a strong acid. So let's write that somewhere. High values of Ka. So what that means is if you have a value of, let's say, 1.6 times 10 to the power of minus 5, which is ballpark the value, the real value I think is 1.76 times 10 to the power of minus 5 for acetic acid. And I'm going to use another one, maybe 3.1 times 10 to the power of negative 10 for HCN. Since it's a negative power, hopefully everybody can quickly relate that that's a smaller number. So one can safely say that the first number that I wrote, 10 to the power of minus 5, that's going to be a very, very larger number as compared to 10 to the power of negative 10. And that would mean that acetic acid is a stronger acid than HCN. Okay, now, is there another way to see the same thing? And the answer to that is, of course, yes. What if you take the negative logarithm of this? So if you take the negative log of Ka, so negative log of Ka is denoted by the small letter p, and we will call it a pKa. And that would mean a smaller value for 1.76 times 10 to the negative 5. That value will come out to be, it'll be to the tune of 4.76 or so. And the 10 to the negative 10, that probably will be roughly like 9 point something, approximately 9.7-ish. And so that will tell you, that will give you an idea that lower the value of pKa and better is the acid. So the rule is low pKa or high Ka implies stronger acid. Stronger acid. And this rule is going to go a long way. If you have to take organic 2 as well, we are going to keep referring to the pKa values, and that's pretty um, important from the perspective of pharmacy as well. The first year of pharmacy school, you would be learning a lot about Kas and making distinctions between structures and pharmacophores and drug candidates. Also recall from Gen Chem 2 that the product of Ka and Kb that gives you, for the conjugate pair, that's equal to the ion product. So if you don't know the Ka value, let's say, and you know the Kb value for the corresponding base, you can use this relationship to determine the Ka and hence be able to figure out information about a certain acid. So keep that in mind. So what I'm saying here is, let's say you want to determine the Ka of ammonium, and that value is not provided to you, but the Kb for ammonia is given, which is the corresponding conjugate base. Then all you have to do is, let's say this value is 1 times 10 to the power of negative 9. So then what you can do is you can simply divide 1 times 10 to the power of negative 14 by 1 times 10 to the power of negative 9, and that will give you the value for the ammonium ion, the Ka value for the ammonium ion. All right, let's talk about this reaction over here. I'm going to make some room, erase some of the things so you can compare, contrast. Let's say my given reaction is acetic acid plus methylamine, CH3NH2, which is giving you acetate and methylammonium ion. Now, my job is, let's say, to label what is the acid, what is the base, what is the conjugate acid, and what is the conjugate base. That's the first thing I'm supposed to do. Again, you just go back to the definitions of Bronsted Lowry acid and base. So a proton donor is going to be an acid, proton acceptor is going to be a base. So as I'm comparing, I would say, well, acetic acid, and if I compare that to acetate, it has lost this proton over here, and so that should be my acid. Likewise, methylamine, and you compare that to the corresponding species that gets generated, looks like I have an additional proton. That means this must be the base. What becomes of the acid upon the loss of the proton will be called as the conjugate base. What becomes of the base upon acceptance of that proton will be called as a conjugate acid. Now, that's how you would label what's acidic, what's basic, what's the conjugate acid, and what's the conjugate base. Now, a lot of times you might be asked, as you would be in the upcoming assignment as well, as to, in the equilibrium, which particular species is going to predominate. So, for example, at equilibrium, whether it is the reactant side or the product side, which is going to predominate, or in other words, is the forward reaction favored over the backward reaction, or vice versa. And that's what we are going to spend some time on. Now, realize when we're thinking about equilibrium, there is a forward reaction, there is a backward reaction associated with that chemical equation overall, and ultimately it just depends on what is more stable. So what is more stable is what predominates at equilibrium. At equilibrium. That means that's going to exist at equilibrium. Whatever is more stable, less reactive is the species that's going to exist at equilibrium. So, in other words, in this particular case, if you had to compare, what you could do is you could compare the acidity of acetic acid versus the acidity of the methyl ammonium ion, and you can compare which one of them is a better acid. The one that is a better acid would want to donate that proton and itself want to stay in the deprotonated form. So now you're questioning which one is a better acid or which one is a more stable base. If acetic acid is a better acid, it would give off that proton and exist as acetate, and that would mean that the forward reaction should be the more predominant reaction. On the other hand, if methyl ammonium ion is your better acid, then that is the species that's going to go through the reaction, and the backward reaction is going to be the more predominant one, and so essentially undissociated acetic acid and methylamine would exist in solution. Now, when you have to make a choice, there are several different factors to think about before you can decide. So I'm going to take the time to go over each of them, and then based on that, we will make some selections. There are several things to keep in mind. The electronegativity, if you're comparing the hydrogen connected to atoms which belong to different groups, that's a pretty important factor. Likewise, if you're comparing within the same group, how would the atomic size alter the acidity of hydrogen? That's an important one as well. And then, of course, the resonance stabilization of the conjugate base. That's an important feature as well. I'm going to give you examples, and we are going to go over every single one of them. In my head, I look at it as cardio. CARDIO. These are the basic sort of rules that you must keep in mind when you are deciding the acidity of the compound. C is for charge. What that means is that if you have a positively charged species, that automatically is going to be acidic. If you have a negatively charged species, that's going to be basic. A stands for the atom. So the nature of atom. And this will cover the size and the electronegativity within it. R stands for resonance stabilization. Resonance stabilization of the conjugate base. Di are together, and that is for dipole induction. And I'll tell you in a second. We are going to go through all of these categories. Dipole induction. And O is for orbital on which the negative charge will be placed. Negative charge will be placed. Of course, when the loss occurs. All right. Let's talk about charge. If you have a positively charged species and you're comparing it to a neutral species, and when I say that, you have to compare apples to apples, not apples to oranges. So if you're comparing, let's say, hydronium ion, you should compare it to water. And let's compare it to a negatively charged species, which is OH negative. Now, you know that water is the conjugate base of hydronium ion and hydroxide is the conjugate base of water. Now, if somebody asks you, well, which one is more acidic, automatically you're going to say that hydronium ion is going to be the better acid. And the reason for that is because the positive charge resides on this species. Now, if you just go back, a couple slides and kind of go back to reflect on the example that I gave you earlier, which was acetic acid, which was reacting with methylamine, and giving you acetate and methylammonium. And somebody might say, well, there's a positive charge here and there is a acetic acid, which was the acid here. So since acetic acid is neutral, there's no real charge on that. That probably is the weaker acid. And you can't really do that because the reason for that is because then you would be comparing apples to oranges. The positive charge here is on the nitrogen atom. So you can't really just compare positive to negative. You also have to see where that positive charge is and which particular atom is holding. Some atoms hold a positive charge a little bit better than others. So you have to keep that in mind. So again, if you have a positive charge, that always will be a better acid as compared to the neutral species, provided you're comparing the same atom in question. So for example, hydronium is going to be more acidic than neutral. Ammonium is going to be more acidic than ammonia, so on and so forth. Anytime you see hydrogens that are connected to or close to a positive charge. So for example, let's say you have a carbocation, and I'm just going to number it 1, 2, and 3 so you can follow along. If you're looking at the hydrogens that are at position 2 against the hydrogens that are at position 3, consider a positive charge as an electron sink. So closer you have hydrogen atoms which are closer to the positive charge, more acidic they would be. So the hydrogen atoms at position 2 are a little bit more acidic as compared to the hydrogen atoms at position 3. So greater is the distance, the effect is going to die down. So that also is one of the things you should keep in mind when you're considering charge. Let's consider the next factor, and that. So what do we know about the atoms? This particular feature is going to be pretty pertinent to those situations where the hydrogen that is supposed to be lost is connected directly to an electronegative atom. So for instance, if we compare hydrogen in CH4 to hydrogen in ammonia to hydrogen in water and hydrogen in hydrofluoric acid. Notice it's the hydrogen atom that is common for all of these 4 compounds, and the thing that is different is carbon versus nitrogen versus oxygen versus fluorine. And if you think about what they differ in, all of them belong to the same period, but they are different groups. So what that means is as you're moving in the periodic table to the right, the atomic size is going to decrease and the electronegativity is going to increase. So greater is the electronegativity, better is the acid. Better is the acid. And this rule holds true provided your comparison is being made. Your comparison that is being made is varying among different groups. So different group elements involved involved. So, in terms of acidity, you would say hydrofluoric acid is more acidic than water, which is more acidic than ammonia, which is more acidic than methane. And the reason for this is that essentially as the bond with hydrogen, as that tends to become very, very polar, that means there is a lot of charge separation between HF, for instance, due to the difference in the electronegativity, essentially the hydrogen will become positive and it will be easy for it to leave. It will be easy for the bond to break. So as the electronegativity increases to the right hand side, essentially the acidity of that particular compound will also increase, and that will automatically mean that the basicity of the corresponding conjugate base is going to be in the reverse direction. That means the F minus, the fluoride ion, is going to be a weaker base as compared to the hydroxide, which is going to be a weaker base than the NH2, and of course the CH3 with a negative charge is going to be most basic in nature. So most basic meaning most reactive as well. Most reactive as well, and the F negative is going to be least reactive or most stable. Least reactive. Based on this, we can perhaps try out an example. Let's say you have HF. Let's say your equation is HF, which is reacted with hydroxide. Your products given are water. I'm going to write water as HOH, and F negative is generated. And you're asked, well, what is the acid? What is the base? What is the conjugate acid? What is the conjugate base? So let's take a look at that. You would say HF is hydrofluoric acid. So that is your acid, which is reacting with the base hydroxide. What becomes of the acid is going to be your conjugate base. What becomes of the base is going to be your conjugate acid. So we have labeled our reaction. Now, the next question is, well, how do you know whether the forward reaction is more predominant or whether the backward reaction is more predominant? And in order to do that, you have to make a call in terms of what is a better acid. So you're comparing HF against H2O, which is a better acid. Or you could compare the basicity of F minus and OH negative. So you have HF, which is hydrofluoric acid, and you're comparing that to the acidity of H2O. And we just saw that when you have the proton, which is supposed to be lost, when that is connected to directly to an electronegative element, then you do have to take into account the electronegativity. And in this case, we are comparing fluorine and oxygen. And because they belong to two different groups, the electronegativity will matter, and greater is the electronegativity, higher will be the acidity. So HF is your strong acid. This is a stronger acid as compared to water. And when you're thinking about that, of course, your HF, which is a better acid, is going to lose the proton more readily as compared to water. And when you do that, you would say that the forward reaction should be more predominant as compared to the backward reaction. So let's write that somewhere. Stronger acid loses proton, and that will react faster. And that would mean that at equilibrium, the HF would have actually lost that proton. And where did that proton go, by the way? That proton has been picked up by the base to give water. So in this particular case, you would say that the forward reaction is going to be more predominant because HF is a better acid than water. Another way to look at it, like I said, you can also take a look at it from the perspective of the stability of the base, in which case you would consider the stability of F minus against OH negative, and we just discussed that as well. F minus is a more stable base as compared to OH negative, and again it goes back to the electronegativity of the fluorine atom. Fluorine is going to hold the negative charge a little bit better as compared to oxygen, and that is the reason that that is more stable. And in that case, you would say that again the forward reaction is going to be the more predominant one in this case, and the right hand side is going to exist at equilibrium. While we're at it, if you're comparing atoms within the group, so now it's no longer the electronegativity but rather the size. As the size increases, the hydrogen will tend to be loosely held and the bond will be easy to break. The reason for that is because as the size increases, the bond is going to be longer, and longer bonds are less strong as compared to shorter bonds. Shorter bonds are also stronger bonds. You know that from General Chemistry 1. So as you have a larger sized anion, it's going to have a weaker bond. So HI is going to be a better acid, whereas HF is going to be it's going to be a weaker acid. Just to kind of give you a flavor, HF has a pKa of 4.9ish or so. HI has a pKa of about -10. So it has a very high Ka. In other words, lower the pKa, better is the acid, and that can be seen. So in a test, you can expect pKa's that can be given to you, and you have to explain. So you're given HI, pKa is -10, HF, pKa is 4.9. Explain, account for this difference. So you're essentially talking about the size, and you're talking about how the bond between H and I is going to break easier as compared to HF. So again, larger is the size of the anion, essentially it'll be easier for that bond to break. And again, it goes back to the fact, as the bonding occurs in case of hydrogen, you have your electron in the 1s. In case of iodine, the electron is present in the 5p. And so since the energies of these two orbitals is so different, it's a long bond and also a weak bond, which can be broken easily. So as the size increases down in the group, within the same group, the acidity increases. So if you're comparing, let's say, ammonia is being compared to phosphine. Phosphine is going to be a better acid as compared to ammonia, and the reason for that is because phosphorus is bigger in size as compared to nitrogen. Likewise, you can compare maybe H2O versus H2S. So H2S is a better acid as compared to H2O because sulfur is bigger in size as compared to oxygen. So we have done C, the charge, so positive charge, better acid. We have done A for atom, and we discussed two things, the size and electronegativity within that. The next thing I want to discuss is R for resonance of the conjugate base within that cardio mnemonic that I gave you. So let's talk about now. Resonance is a very important concept that we have discussed in the past, and basically that means delocalization or smearing of electronic charge. Now, if that is existent in a certain conjugate base, automatically that would mean that it would be a very stable conjugate base. And so if your conjugate base is being stabilized by resonance, go for it by all means. That is going to happen, and that is going to be your more predominant and more stable situation right there. Let's take a look at some of the some of the examples that I wanted to give you. So let's say I have ethanol, I have acetic acid, and I have methyl sulfonic acid. Of course, when you're drawing the Lewis structure, don't forget about the lone pair of electrons, because that's what you will need to show your resonance. And your question is, well, in this case, I'm kind of showing you already that methyl sulfonic acid is a stronger acid as compared to acetic acid, which is a stronger acid than ethanol. The same thing could be given as pKa of ethanol is, let's say, 18. pKa of acetic acid is 4.8. pKa of methyl sulfonic acid is -2. Suppose, okay? And you have to explain why is this so. Like I said, we are discussing resonance. One can say that if once this proton has been removed and you have the negative charge, if that negative charge is better stabilized in one structure than the other, you can say that that particular reaction is going to be faster. So we really are comparing that you have methyl sulfonic acid, CH3S double bond O, OH, which let's say it's reacting with water, and it's giving you O negative and hydronium ion. So what we're saying here is methyl sulfonic acid is a good acid, and the reason why it's a good acid is because it readily gives off that proton to the water molecule, and in doing so it's generating a negative charge, and so this corresponding conjugate base is more stable than the corresponding conjugate base of, let's say, acetic acid. The reaction in that case is going to be acetic acid plus water gives you CH3 COO negative plus H3O plus, and the third reaction is CH3CH2OH plus H2O. We are trying to say that we are going to get CH3CH2O negative plus H3O plus. Again, when you have to say which one is acid, which one is base, you say the one that loses the proton is going to be your acid. It reacts with a base. What becomes of the acid is going to be your conjugate base. What becomes of the base is going to be your conjugate acid. So this negatively charged species is what we are talking about. And we are saying that if methane sulfonic acid has to be the best acid, that would automatically mean that its corresponding conjugate base should be most stable. Let's see if we can actually prove that. Notice what's going on. You have sulfur, which is connected to an oxygen through this double bond. What can happen? Oxygen, being more electronegative, is going to pull electrons towards itself. Guess what? There is a negative charge which is present at this mobile pi system, and it's only one single bond away. That means it's at an alternate position. So according to the principle of resonance, as the electrons move, these electrons can kick in. So you can draw another structure where you have CH3, sulfur has an O negative, you have a double bond O, and you have a double bond O right here. What else can happen? Essentially, this negative can kick in, and the negative on the oxygen will kick out. That will give you another structure, CH3, S double bond O, and oxygen with a negative charge. Of course, this can kick back in, and now you can incorporate the movement of the pi system back again, which will give you the same structure that you began with. So one can say that methane sulfonic acid, the conjugate base of that, has 3 resonance structures. Likewise, if you do the same thing for the acetate unit, the electrons will kick in, these electrons will kick out, and that will give you CH3CO negative. It will give you this structure. That contains 2 resonance structures. And if somebody asks you how many resonance structures do you have in ethoxide, yes, you got it right. There is no pi system, so there is no resonance. The negative charge on oxygen is localized. There is no smearing or delocalization of that charge, so it's pretty reactive. And you would say no resonance in that case. No resonance. Resonance. Rule of the thumb is more is the number of structures, resonating structures, higher is the amount of resonance, or greater is the stability. So more resonance structures implies more stability. And that is the reason that methane sulfonic acid, the conjugate acid for that, conjugate base for that, is more stable than the acetate, which is more stable than the ethoxide. And that is the reason why methane sulfonic acid is a better acid as compared to acetic acid, which is better than ethanol. Based on this, what I want you to do is come up with the order of acidity for HClO versus HClO2 versus HClO3 versus HClO4. That is perchloric acid compared to chloric acid compared to chlorous acid, and finally compare it to hypochlorous acid. If you can draw the structures and if you can explain that, you're all set. I'll give you the answer to that. It really is least acidity for hypochlorous acid and maximum acidity for the perchloric acid. That's the order, but I want you to draw the lowest structure, explain via resonance, and explain why that happens. Okay, so this was R for resonance. The next one is dipole induction. That's the next. Let's talk about dipole induction. Dipole induction. All right. Let's consider first acetic acid. Okay. CH3COOH. And if you're asked, circle the most acidic hydrogen, which one do you think you're going to circle? Yes, that's right. You would go with the H right next to oxygen. Recall that it is the one which is connected to an electronegative element. If you compare that to carbon, carbon is less electronegative. So even though you have 3 hydrogens over there, those are not acidic or as acidic as the hydrogen next to the oxygen. So that's the first thing. Now, let's say you have a fluorine atom connected to acetic acid. So it's fluoroacetic acid. Or whether you have difluoroacetic acid. And we are still comparing the acidity of the OH when compared to acetic acid. Which one do you think is going to be most acidic? Realize since fluorine is electronegative in nature, it's going to pull electrons towards itself, which in turn is going to pull the net electron towards fluorines to a greater extent than when you have only one fluorine atom, than when you have no fluorine atoms. Whenever you have more electronegative atoms connected or in close vicinity, the acidity of the proton in question, that is going to increase. So C is going to be most acidic, followed by B, followed by A. You can view it in another way. How about I compare fluorine to, let's say, chlorine. Notice your atom that is going to be lost, which is the H, is connected to oxygen, and it is also connected to oxygen in this case. So that is not the part which is being changed. What is being changed is the drive, the overall pull of the electron in the second case as against the first case. So since Cl is less electronegative, it will pull, but to a lesser extent as compared to when pulled by fluorine. So the structure that I drew in blue, which is chloroacetic acid, let's call it maybe B2. That's going to be less acidic as compared to B1. So B1 is more acidic than B2. Likewise, if you would have had a bromine or an iodine, those would have been lesser acidic as compared to the chlorine in that order. Let's consider another scenario. Perhaps have the same atom, but maybe move it away. So keep it at a distance. So rather than having one atom or a direct attachment, let's keep that one atom away. So you still have the same fluorine atom, but it is 1, 2, 3. So at the third position as against 1 and 2. So since the fluorine is far away, that's right, you would expect the acidity to go down since the fluorine is at a distance. So let's call it B3. B3 is going to be less acidic as compared to B1. All right, so that was dipole induction. Let's talk about orbitals. This is the last of all, last but not the least, and this has got to do with essentially what happens when you actually lose that proton and you do get a negative charge. Where is that negative charge held? So for example, if you compare an alkyne to an alkene we say that pKa of an alkyne is 25, pKa of an alkene is like 40, and pKa of an alkane is like 55. That means alkyne is most acidic and alkane is least acidic. And the question is, why is that? Well, it kind of goes back to what would you get when you actually lose one of these protons. This is CH2. When you lose one of these protons. In the first case, you're going to end up with the acetylide ion. In the second case, you would end up with a vinyl carbon ion. In the third case, you would end up with CH2 with a negative charge as a carbon ion. So now we are asking the question, where is this negative charge? Where is this additional electron held? Realize when you have a triple bond, it is going to be held in an sp hybrid orbital. In this case, it's an sp2. In this case, it's an sp3. If you think about the kind of hybridization and the amount of percent character, percent S character, that would be 50% in case of SP. It'll be 33.3% in case of SP2. It's only 25% in case of SP3 because one out of the two S and P put together is an S orbital. One out of the three, one S and two P, so one out of three. So a third is an is an s character, and 1 out of the 4, the 1s and the 3p orbitals, so 1 out of 4 has an s character, and you would say that it's only 25%. Turns out, recall from General Chemistry 1, that p orbitals are more directional. P orbitals, those are directional. So they have a sense of direction. Whereas s orbital, because the shape is spherical, they essentially are uniform. So they are symmetric. And since they are symmetric, they also cover the orbit a little bit better. And so since they are uniform, since they are symmetrical, they actually hold this negative charge in a much better sense as compared to the sp3 hybridized orbitals, which is why the carbon ion in case of ethane is going to be very reactive, and in case of the acetylide it will be very stable. And since it's stable, you would say that in that particular situation your reaction is going to go in a direction such that it aids the stability of your your alkynyl anion in this particular case. So that's cardio. Those are the various different things, various different factors that you have to keep in mind. We are going to try to apply these in specific cases, and so I'm going to take you back to the question that we had posed this discussion, which was acetic acid reacting with methylamine, remember that, giving you acetate and methylammonium, CH3NH3 plus. And I told you that you have to compare the acidity of the two acids or the basic character of the two bases and go from there. So if you were to compare the basic character, you have methylamine, the lone pair is present on nitrogen. You have acetate, which contains resonance. What did I tell you about resonance? I said whenever you have resonance, go for it. That is going to be most stable. So one can say that the acetate, because it has resonance, it is going to be more stable as compared to the localized lone pair of electrons in case of the methylamine, which is why acetic acid would want to spend its time as the acetate as compared to the undissociated acetic acid form. So in this case, what's going to happen is that acetic acid is acidic enough that it can actually protonate the methylamine and give you the methylammonium and the acetate unit. Forward reaction is going to be slightly more predominant. And if you compare the pKa's, the pKa of acetic acid is about 4.76. The pKa of methyl ammonium is close to about 7 to 8. So it is about 1,000 folds or so more acidic as compared to the methyl ammonium species, and that is going to be a better acid. Okay, let's try another one. Let's say you have HF, which is reacted with NO3 negative, and that gives you HNO3 and F negative. So you can say that you have over here two bases, F minus and NO3. NO3 of course is going to have resonance. We talked about that in previous videos where the last electron is shared between the three. So this is going to be more stable, and that automatically also is reflective in the fact that nitric acid is a strong acid. It's an ic acid as against the hydrofluoric acid. It is one of the weaker acids, and that tells you that nitric acid would want to spend its time more as the nitrate unit. So the backward reaction is going to be the more predominant reaction, the favored reaction in this case. And at the end, once the equilibrium is set up, the species in question would be HF, and the nitrate that would exist, not nitric acid and fluoride. So either you can compare the stability of the conjugate bases, or you can compare the acidity of the acids to prove your point. So again, weaker acids or more stable acids are the ones that predominantly exist at equilibrium. Okay, let's go forward. Question right now is, which of the following is the strongest acid? You are given some pKa values: pKa 33, negative 2.2, 15, and 4.74. You know, lower the pKa, stronger is the acidic behavior. So HCl is your appropriate answer. Hopefully you were able to get that. All right, the last thing I want to talk about is Lewis acids and bases, and kind of connect that to what electrophiles and nucleophiles are. So far we began our discussion as Arrhenius acids being proton donors. Bronsted and Lowry kept that definition, said that Bronsted and Lowry acids will be proton donors. Lewis actually took it one step further, and this is actually the most modern definition of acids and bases. Essentially, because Bronsted and Lowry and Arrhenius were restrictive to protons only, anything which did not contain protons could not be classified as an acid, and things like BH3, for example, or BF3, boron containing compounds, they did have acidic behavior, but they were not classified as anything. And at that point of time, Lewis basically provided this new definition, the more modern definition, according to which acids will be those species which accept electrons, or electron deficient species. Electron deficient species are Lewis acids. So when I use the word electron deficient, that automatically means BH3 or BF3, whichever you want to draw the structure of. Notice that the maximum number of electrons around boron is 6, and you want 8. So at any given point of time, boron would willingly accept electrons, and hence all boron containing compounds are Lewis acids in nature. Since they have an affinity for electrons, they are also referred to as electrophiles. Phile for love, electro for electron. Opposite of that would be bases. So bases will donate electron pairs. So things like ammonia, which has a lone pair of electron, will be called as a Lewis base. And since it will have an affinity for something which is positively charged or something which has a dearth of electrons, you would call it a nucleophile. So those electrons can be given to this proton so that it gives you ammonium ion. So one can say that ammonia is both a Bronsted-Lowry base as well as a Lewis base, because it has this lone pair of electrons that can be given to the proton to form that ammonium ion. And over here, I'm showing you, let me erase this so you can see for yourself. Maybe I'll just rewrite again at a later point. So I'm giving you an example that you have methoxide, which is being treated with methyl chloride. Notice the electrons are moving from the negatively charged species onto the carbon. And I know that carbon is the one that is a positive species because chlorine is more electronegative, so it's going to pull the electrons towards itself, leaving a positive charge on carbon, which is your carbocation. If somebody asks you, where is the electrophile? Well, the electrophile is on the carbon because the CCl bond is a polar bond. So that's going to get attacked by the negative charge on the oxygen, which is going to behave as a nucleophile. Your end game, your end product is going to be a new bond between carbon and oxygen, and Cl would leave. That is your leaving group. Okay. So again, electrophiles, these are electron poor. They could be neutral, such as the case of BF3, BH3, or they could be partially positive, so a methyl carbocation, or even a proton. Those are electrophilic in nature. Nucleophiles, on the other hand, are electron rich, so you would usually see a negative charge like a hydroxide or an F negative, or they could be neutral like ammonia or water, because they have the lone pair of electrons, so one or the other. The main point is that these should have mobile electrons either through a pi system, lone pair, or maybe even a negative charge if it's a negatively charged nucleophile. So over here I'm showing you a lone pair of electron on ammonia that is attacking the boron. So notice it's always going to go from source to sink. Where the electrons are, that will be your nucleophile, and the sink will be your electrophile. So always negative to positive. That is how you're going to show the movement of electrons, and that is how we will continue this discussion sort of to write mechanisms of reactions as well. So if you can remember this, that electrons always move from negative to positive, from electron source to electron sink, from nucleophile to electrophile, you should be set. All right, the question is, which of the following is an electrophile and why? And hopefully you're thinking electrophile means something which is a positively charged species. Here you have your lone pair of electrons. Here you have your negative charge. You have a negative charge here. That's your positive charge. That should be your final answer. Okay, based on this, I want to just, kind of apply things together again so we know what's going on. And I'll take a very simple one. Let's say you have hydronium ion, H3O plus, which is reacting with ammonia and giving you water and ammonium ion. And you're asked, well, say which one is acid base, acid, conjugate base. And also establish which direction is the equilibrium going to be in. Hopefully you can see positive charge, that's your acid, this is your base. What remains of the acid is your conjugate base. What becomes of the base is your conjugate acid. So all positively charged species are acidic in nature. And now you have to compare the acidity of the hydronium against the ammonium. And whichever is a stronger acid is going to donate its proton. Or you could look at the stability of the bases, which is ammonia against water, and whichever is more stable is what is the one that's going to remain at equilibrium. Realize that you have, in case of hydronium, if you draw the Lewis structure, the positive charge is present on a more electronegative element, such as oxygen, as against ammonium, where the positive charge is located on nitrogen atom. And by rule, a less electronegative element is going to hold the positive charge a little bit better than the more electronegative element. So this oxygen is kind of unhappy. That's what we are saying, that this oxygen holding 3 bonds and getting a positive charge, it's kind of unhappy. It doesn't like that positive charge, and it would want to get rid of that proton pretty quickly. And that's evident in its pKa, because the pKa of hydronium ion is close to about negative 1.5. On the other hand, the pKa of ammonium is almost 9. So that gives you an idea that since hydronium ion is a better acid as compared to ammonium ion, it would want to get rid of that proton and become a water molecule. And since ammonium is the more stable one, that is what is going to exist at equilibrium. Another way to view the same thing would have been that you have lone pair on nitrogen, you have lone pair on oxygen. In case of water, which one of them is going to be able to donate those lone pair of electrons? And the answer is again nitrogen. Since it's less electronegative, it would be more willing to share that lone pair of electron. So the way the reaction would take place, if somebody asks you, well, push the arrows, what would you say? You would say that you have NH3 with the lone pair of electrons, which is your nucleophile, which is going to seek that proton. Electrons are going to go on oxygen, and you end up with water and ammonium ion. And that is it. Two arrows that tell you everything about how the reaction proceeds. So let me just complete this. NH4, 4 bonds with a positive charge on nitrogen, and water that left is going to be your conjugate base.